Hi, in this video, I'm going to go through the AQA A-Level Chemistry Paper 2 from 2019. And this is the second half of the paper, starting at question 8. I covered the first half in an earlier video. Okay, right, here is a question about organic synthesis, making paracetamol, okay, from in the 3 stages shown there in the diagram. Okay, name the mechanism of the reaction in step 1. Well, what are we doing in step 1? We're sticking on a nitro group, an NO2 group, onto a benzene ring. And of course, benzene undergoes electrophilic substitution reaction. So that's what it is. It's electrophilic substitution. Now, it doesn't ask you what the electrophile there would be. NO2, of course, NO2 plus, generated from conc nitric and conc sulfuric acid. All right, complete the equation for the reaction in step 2. Okay, so what we're doing in step 2 is you can see, we are getting that NO2 group and we are reducing it to the NH, to the amino group. Okay, and so in these kind of reactions, they want you to show the reducing agent as hydrogen in a square bracket. That means a hydrogen atom. Okay, so let's do that. Right. Okay, so what is going to happen to these oxygens? They're going to end up on the other side of the equation as waters. So that's going to be H2O there. We're going to need 2 H2Os. There's 2 oxygens to get rid of. Now, how many extra hydrogens have we got? Well, on the left-hand side, the right-hand side of the equation, we've got those hydrogens extra and those hydrogens. That's 6 hydrogens extra. So that means we need a 6H there. Okay. The reducing agent there, of course, would be tin and hydrochloric acid, but it doesn't ask you that. Okay. In theory, either ethanoyl chloride or ethanoic anhydride can be used in step 3. Complete the mechanism. Okay, so we've got to do that here. And you're showing the amino phenol thing as just R. Right. This mechanism, of course, is nucleophilic addition elimination. Okay, so the nucleophile is the NH2 group. The lone pair goes onto the delta positive carbon. Okay, so the intermediate we're going to form there is going to look like this. And have a negative charge on the oxygen. We have now got the chlorine is still attached, and we've now got the nitrogen. Right, now that nitrogen is going to have a positive charge on it. Okay. The next step in the mechanism is the double bond is going to reform. So we need to draw 1 lone pair on the oxygen there. And the curly arrow, that's going to go in to make the pi bond. And at the same time, the chlorine is going to leave as a chloride ion. So we have now got almost there. Right, and the final step, which you can actually combine in that one there, but I prefer to do it separately, is that nitrogen loses a proton. So the bonding pair here goes back to being a lone pair on the nitrogen, and we end up with the final product. As I say, you can combine those last 2 steps into one if you want. Right. In practice, ethanoic anhydride is used rather than ethanoyl chloride. Right. Give one reason why it's not used. Well, if you use ethanoyl chloride here, so I should put the mechanism here. We end up with a Cl minus there and an H plus here. You end up making HCl gas, which is corrosive. Okay, so if you use the ethanoyl chloride, you make HCl gas. That's corrosive. That's the answer I would choose. Incidentally, what you wouldn't make HCl if you use it at the the anhydride, you would make ethanoic acid, which is less corrosive, okay? But it doesn't ask you that. If you didn't want to say that, you could say that ethanoyl chloride undergoes hydrolysis easily. So it goes off quickly. Got to keep it away from water vapor, or it'll hydrolyze. The acid anhydride doesn't do that to the same extent. But I'd probably just go for the HCl corrosive as the answer there. Okay, in step 3, other aromatic products are formed as well as paracetamol. Okay, I just copied step 3 there. So what step 3 was the nucleophilic addition elimination reaction, where basically we stuck on that acyl group onto the nitrogen. Well, ethanoic anhydride and ethanol chloride, they also react with the hydroxide group there, okay? They will also acylate that. So another product you could get would be, I would say we've acylated there. Sorry. And we've also acylated it here to form an ester linkage. Okay, so that would be the answer they're looking for there. Right, chemists have recently developed a 2-step process to produce paracetamol from phenol. In the first step, the phenol is oxidized to hydroquinone here, and then it reacts with ammonium ethanoate to form paracetamol. Complete the reaction with the second step. Right, let's write down the equation, the formula ammonium ethanoate. So here's the ethanoate ion. And the ammonium ion, of course, is NH4 plus. So I put in there CH3 COO minus NH4 plus. Now, you can probably see that to balance that equation, all you need to do is you've got a few extra oxygens and hydrogens, they're going to form water. So we're going to put an H2O there. Now, how many H2Os are we going to? You can see that we have got 3 oxygens there. We're down to 1 oxygen there. So that's going to be a 2 in front of that. And if you look here, you've got 4 hydrogens there for the water. That balances. Okay. If you're ever looking for another thing to balance an equation, water is very often one of the products, so always look out for that. Now we have a calculation, it's like a yield calculation essentially. So calculate the mass in kilograms of hydroquinone needed to produce 250 kilograms of paracetamol. It doesn't say so, but presumably they're talking about a 100% yield. Right, so we need to work out the MR of paracetamol. Okay, so we just look at the paracetamol here. Got to be careful that you don't miss any hydrogens off or anything here. But how many carbons have we got? We've got 6 in the benzene ring and that one, so that's C8. Hydrogens, well, we've got 1, 2, 3, 4, 5, 6, and 3 there, that's 9. We've got 1 nitrogen and we've got 2 oxygens, so that's we should put the oxygens first. Add all that up and you get the MR is equal to 151 for paracetamol. Okay, so the mass of paracetamol is 250 kilograms. That's equal to 250 times 10 to the 3 grams. Okay, so moles paracetamol. Mass over MR. That's equal to 250 times 10 to the 3 over 151, which gives that number. Okay, that many moles. Now, if you look here, 1 mole of hydroquinone gives you 1 mole of paracetamol. So that means the moles of hydroquinone we're going to need is the same. (1655.6). So the mass of the hydroquinone is going to be equal to the moles multiplied by the MR. The moles is 1655.6 multiplied by the MR, which they tell us is 110, which gives us 1.82 times 10 to the 5 grams. We ask us for the mass in kilograms, so divide by 1,000, that is equal to 182 kilograms. And that's the three significant figures. Our least accurate bit of data is to 3 sig figs, so that's what we should do. Okay, right, here's a question about thin layer chromatography. So you get a protein hydrolyzed and it makes a mixture of amino acids. Okay, so what they have done here, they've done a two-dimensional TLC. So first of all, they put the original spot of protein on there, of hydrolyzed protein, and they have run the chromatogram in that direction. And then they've turned it around and then used this kind of line, this green line, as the start line, and then they've run it in that direction. Okay. So two-dimensional TLC. Right. So a suitable reagent for the hydrolysis of a protein, the best thing to use would be conc HCl. Right. You want an acid. Sulfuric acid might end up sulfonating some of the side chains. So hydrochloric acid is the acid of choice there. Right. Suggest how the positions of the amino acids on the TLC plate were located. Well, amino acids are, you won't see them, they're not colored. So there's two ways. The best way is you spray with ninhydrin, chemical called ninhydrin. Let's make sure the spelling's right. Spray with ninhydrin, and most of them turn into a purpley spot. Alternatively, you could view under UV light. Right. So either one of those. Now it's going to ask us about two-dimensional thing. Deduce the minimum number of amino acids present in the original mixture. Okay, so let's see what's happened here. In the first direction, solvent one direction, you get those 3 spots. Now those 3 spots, well, this top one is just one amino acid, but you can see that one there. When you run it with the second solvent, you end up getting 2 separate spots. Okay, and the same with that one there. That one gives you 2 separate spots. And there is also one amino acid which doesn't, one of them doesn't move in solvent 1 at all, but it does move in solvent 2 to give you those 2 spots there. So let's just add up all the spots we've got. You have got, so the final, so you've got 1, 2, 3, 4, 5, 6. There are 7 spots, 7 different amino acids in the mixture. Right, that's a question for 9.3. Suggest why it was necessary to use 2 different solvents, 9.4. Right, the reason why is because, like for example, these 2 amino acids have the same RF value. They move the same distance in solvent 1. So you can't distinguish them using solvent 1 alone. You need to use solvent 2 to separate it out because they have different RF values in the solvent 2. Right. Question 10. Some compounds with different molecular formulas have the same relative molecular mass to the nearest whole number. A dicarboxylic acid has a relative molecular mass of 118. Deduce the molecular formula of the amino acid. Okay, so it's got a dicarboxylic acid, so you're going to have that on each end. Now that bit, each of those weighs, each of carboxylic acid, so 32 plus 12 plus 1, that is going to give you 45. So 2 times 45 gives you 90. The total molecular weight is 118. So 118 minus 90, what have we got in between those? That's 28. But you can probably see that's like having two CH2. They weigh 14 each. We've got 2 of those. So it's butane dioic acid we've got there. Now, as for the molecular formula, I haven't drawn the molecular, that's the structural formula, molecular formula, so we need to write down how many carbons. There are 4. How many hydrogens? We've got 1, 2, 4, 6. How many oxygens? We have got 4 oxygens. So that's the molecular formula, C4H6O4. Now we have a titration question here. So a student dissolves some of the carboxylic acid in water made up to 250. So here is our 250 volumetric flask. We're going to take 25 of that out. And we're going to titrate, sorry, we're not going to take 25 of that out because that is going to go into the, oh, we are. Yeah, we are. That's going into the conical flask. 25 sample of the acid is going into the conical flask. And then we're going to titrate against NaOH. And we need 21.6 centimeters cubed of NaOH of 0.109 mole per decimeter cubed. What we're going to do is calculate the mass of the acid that we put in there. What mass have we put in the flask? Right, we need to think about the ratio in which it reacts with sodium hydroxide. Well, it's a dicarboxylic acid, so then have that. Right, that is going to react. You've got 2 protons to remove there, that one and that one. So you're going to need 2 NaOHs to react with that. And that will give you the negative ion there, negative ion there. Okay, so the important thing is we've got the ratio, mole ratio is 1 acid to 2 NaOH. Okay, so let's work out our moles of NaOH first, which we can do because we know the volume and we know the concentration. Let's do that. Okay, moles of NaOH. Conc times volume. The concentration is 0.109. The volume is 21.6 over 1,000. That gives us 2.35 times 10 to the minus 3 moles of sodium hydroxide. Now we've got this ratio is 1 acid to 2 sodium hydroxide. So the moles of acid is going to be half that. So the moles of acid, and that's in 25 centimeters cubed. Don't forget here. Is equal to that divided by 2. Which is equal to 1.177 times 10 to the minus 3. That's how many moles of acid we've got. Now, that's in 25. So I'll go up here now. So moles in 250 is going to be 10 times that. So that's going to be 1.177, multiply that by 10, gives times 10 to the minus 2. The question, it asks us to find out the mass of the acid. So mass of the acid is equal to the moles of the acid multiplied by the MR. We've just worked out the moles, that's 1.177 times 10 to the minus 3. The MR of the acid, they told us, was 118. So that gives us 1.389 grams. Let's give that to 3 significant figures, because it asks us. That's 1.39 grams is the answer. We should give it to 3 significant figures because the data was all given to, you look at the data in the question, that's mostly given to 3 significant figures. Okay, continuing on with compounds with a relative molecular mass of 118 to the nearest whole number. This includes a diol. Okay, deduce the number of peaks in the 1H NMR spectrum of this diol. Now, there's quite a bit of symmetry in that molecule there. So you can see that those protons there are in the same environment as those. So that's 1 peak. The 2 alcohols are in the same environment, so the symmetry, so that's 2 peaks. And then these, they're in the same environment again because of the symmetry, so that would give us 3 peaks. Okay, draw the structure of a different diol, also with a molecular formula with molecular formula C6H14O2, that has a 1H spectrum consisting of 2 singlet peaks. Okay, so we can see it's a diol and there are no double bonds in that because look at the ratio, it's CnH2n plus 2, no double bonds. Right, now there is only going to be 2 singlet peaks. That means when you've got 6 protons and you've only got 2 peaks, there must be quite a bit of symmetry going on there to make it so that you don't have that many peaks. Also, I would 2 singlet peaks. Let's have a think. So that if you had something like that, that would get rid of that would mean, okay, those protons are all the same. So we've got rid of, but I don't think that's going to work. Okay, that would give us a singlet peak. What else have we got there? We've got 2 other carbons to think about. That's not going to work because saying if this was H, OH, HO, that's not going to work. There's too many peaks. So I don't think we've got that arrangement there. But I do think we're going to have something like this. I think we've got 2 of those in the molecule. So let's put 2 next to each other. That will work. The singlets, you're going to have the 2, they're the same. That will give you 1 singlet. And then all of these peaks, they're all the same as each other, those CH3s. And the carbons to which they're attached, these 2 have got no other hydrogen, so they're not going to be split. They will be singlets. I think that's the only thing you can have actually for that. Right, 10.5, the dicarboxylic acid in question 10 and the isomers all have a relative mass of 118. State why the dicarboxylic acid can be distinguished from the 2 diols by high resolution mass spectrometry. All right, and the reason for that is because they have got different molecular formulae. And that's all you need to say. And you need to say that just to explain, because you've got different molecular formulae. For example, carbon, oxygen doesn't have a mass of, it's not exactly 16. It's actually slightly less than that. And hydrogen is not exactly 1. It's quite a bit more than 1. Okay, so if you have different numbers of different atoms, they will weigh slightly different amounts. And I think all you have to say there is they have different molecular formulae. Okay, question about esters, including biodiesel. So this is about triglycerides, and these questions are always badly answered because when you're revising this topic, you've got to sit down and draw some of these triglycerides. They look quite complicated. They're not as complicated as they look. All right, sorry, that comes on to the next bit, biodiesel, but nevertheless, it's true. Right, so draw a few triglycerides. Anyway, this ester is formed by the reaction of an acid anhydride with ethanol. What we're going to get, right? So what is going to happen is basically this bit is going to drop off and form a carboxylic acid. So that's going to form CH3, CH2, C carboxylic acid, and this acyl group is going to stick on that oxygen there. Of course, this hydrogen goes off to on the carboxylic acid. So the ester we're going to get is going to be then it's going to be CH3, CH2. That's from the acid anhydride, and then this bit's coming from the ethanol. That's the answer there. Okay, in a reaction to form biodiesel, 1 mole of vegetable oil reacts with an excess of methanol to form 2 moles of an ester with a molecular formula that, and 1 mole of molecular formula that. Okay, draw the structure of the vegetable oil showing clearly the ester links. Right, now let's just do this kind of backwards. When you form biodiesel, you form methyl esters of the carboxylic acids. Long chain carboxylic acids, you call them fatty acids, okay? So let's look at this one. Let's do that in red, and I'll do this one in blue or something, okay? Okay, let's do the one in red, right, C19H34. So we're going to have the methyl, the bit from the methanol. Now, we've used up two of the carbons there, so that's going to be C17 left over. And that means we've used up 3 of the oxygens, so that's going to be H31 for the hydrogens there. Right, and we're going to have, so I should be doing this in red, but I'm not, so let's change the color scheme. I'm going to draw 2 of those. And the other one, which I'm going to draw in red here, okay, that is got 2 more hydrogens than that one. So that's going to be like that, CH3O, C double bond O, C17H, and it's going to be H30. Lost 3, that's 36 there, so it's H33. Right, now they must have come from so that's 3 separate methyl esters. They come from one ester formed from glycerol, which is propane 1,2,3 triol. So I'm going to get rid of those there. And this would have come from glycerol. Glycerol is like that. Just to remind you, glycerol is propane 1,2,3 triol. So each of those OHs form a separate ester linkage. So this is our answer here to that question, okay? And I would imagine that a lot of people got that wrong because people don't really take the time to draw out these triglycerides and get to know what the structures are really like, okay? Right, the compound C19H34O2 is a methyl ester of ZZ octadeca 912 dienoic acid. Okay, part of the structure is shown. Complete the skeletal formulae to show the next part of the hydrocarbon to carbon number 14. And you've got to show the stereochemistry, the Z stereochemistry around both carbon-carbon double bonds. Okay, so we have got a double bond between 9 and 10. So there's 8. Okay, there's 9. There's 10. Right, now that is a Z stereochemistry. So that means it's got to go like that. Okay, we've got the 2 high priority groups on the same side, and the 2 low priority groups, you've got a hydrogen there, and you've got a hydrogen there, haven't you? They're on the same side. I'll get rid of those, but just to show you. So that should definitely show the Z stereochemistry. Now it's also got a double bond between carbons number 12 and 13. So got 10, 11, there's 12. Now 13 is here. And again, Z stereochemistry, so it's going to go like that. Got the 2 high priority groups, and there's carbon number 14. We don't need to draw any more after that. You've got the 2 low priority groups, the hydrogens on the same side, and so that means the 2 high priority groups on the same side, so that's Z configuration there. So that's what you need to draw there. Right, give an equation for the complete combustion of that ester, right? So we've got C19H34O2. Right, that is going to give us 19 carbon dioxides. There's 34 hydrogens, so 34 divided by 2 is 17. We've got 17 waters. And then we've got to count how many oxygens we need for that. Well, we've got 19 times 2 in the carbon dioxide, so that's 38 oxygens plus 17 there. That gives us 55. So half of 55 oxygen atoms, so half of that, you need 26 and a half oxygens. There's nearly always one of those complete combustion balancing equations on a paper, on most papers, if you look, most of these organic papers. Okay, combustion of biodiesel produces carbon dioxide. Okay, that's what we're talking about here. And it shows us that causes global warming. Part of the infrared spectrum is shown there. Okay, so there we've got it there. State how the infrared spectrum of CO2 is not what you might expect from the data booklet table. Right, I've got the data table here. Now, carbon dioxide, of course, has got essentially got 2 carbonyl oxygens there. Okay, 2 of those groups. If you look at the data there, that should give you an absorbance of between 16, 18, 17, 50. So this is actually a lot higher than you'd expect. It's like about 2,000, 2,200 approximately. It's higher than you would expect. Obviously, it doesn't actually, that's only for 1 marker. Just all you have to say it's higher by having that another double bond oxygen next to this one obviously modifies the bond strength, and so the absorbance, the wavelength of infrared it absorbs. Explain how carbon dioxide causes global warming. Okay, it absorbs energy from infrared radiation. And then this energy is transferred to surrounding molecules. All right. Now here is a bit of a DNA molecule. Okay, shows 2 complementary strands in part of a DNA helix structure. Okay, let's see what's going to ask us here. Draw all of the hydrogen bonds between the complementary strands shown. Okay, now here, if you look at your data sheet, you have got, this one is adenine, This one is thymine. This one here is guanine, and this one is cytosine. Right, and now it stays here. You don't need to show any partial charges, and you don't need to show lone pairs of electrons. Okay, so draw them as dotted dashed lines. Use dashed lines. A bit hard to do dashed lines with this pen, but I'll try. So you've got one there. Remember the T and the A, they only form 2 hydrogen bonds per pair. So that hydrogen is going to go to the lone pair on that nitrogen. With G and C, you get 3 lots of hydrogen bonds. The H on there goes to the lone pair on the oxygen on the carbonyl there. This H goes to the lone pair on the nitrogen, and this hydrogen goes to the lone pair on that carbonyl. Okay, so that's that there. Next question. Draw a ring around the component parts that make up a cytosine nucleotide for 2 marks. Right, so we know which one is the cytosine. Remember, a nucleotide is, you have a phosphate, then you have the ribose sugar, and then you have the base. Now, it's important to remember that the phosphate in the nucleotides, right, there's 2 phosphates on this, if you look at this ribose here, and you have to make sure you get the right one. Now, you number the carbon atoms there, 1, 2, 3, 4, 5. Now, in the nucleotide, the phosphate is stuck to the carbon number 5. Okay, so it is this phosphate group up here, that ribose, and the cytosine there. It is not this phosphate group there. That's attached. That would be on the next one along. So that's next. That's on ribose base. Okay, that phosphate originally belonged to the next one. It didn't belong to the cytosine. As I say, the phosphate is always stuck on the 5, carbon number 5 on the sugar, not on the carbon number 3 there. That forms when the DNA polymerizes. Okay, so that's the answer there. State the meaning of the term complementary when it is used to refer to DNA strands. I think all we need to say there is that A always H bonds to T on one strand, and C always to the G on the other strand. Okay, we've got sodium borohydride reduces aldehydes, but does not reduce alkenes. Show the first step in the mechanism of the reaction between NaBH4 and, right, so here we should only draw, the hydride ion. We don't draw the full NaBH4, simplify things, okay? Right, so we need to draw 2-methyl butanal, first of all. So butanal, we need 4 carbons, 2-methyl, so I need to put a CH3 on there. I think I'll simplify that, just call it CH2CH3. Okay, now we need the hydride ion here. Just wants the first step in the mechanism. Right, this carbon here, of course, is delta positive. Okay, we don't need to put in the diagram. The lone pair goes from there to there, and it's nucleophilic addition, and so the pi bond breaks and the pair of electrons go onto the oxygen there. Okay, so that is the first part of that. We don't need to draw the products. Explain why NaBH4 reduces 2-methyl butanal but has no reaction with 2-methyl but-1ene. Okay, now the reason why is because 2-methyl but-1ene this should be H minus, yeah. It's because the H minus is a nucleophile. And you don't have a delta positive carbon on that molecule. no carbon with a partial positive charge on it in butene and 2-methyl-but-1-ene. That's the answer there. NABH4 is a nucleophile, so it's not going to react with alkenes. It's only going to react with ketones and aldehydes. Okay, a student attempted to reduce 2-methyl-butanol but added insufficient NABH4. Okay, the student confirmed the reduction was incomplete by using a chemical test. So basically, if it's all reduced, that will go to the primary alcohol. So you will have no aldehyde left over. So you need to test for an aldehyde. If you haven't added enough NABH4, there's some aldehyde left over. How do you test for an aldehyde? The reagent, well, you can use Fehling's or Tollens. I'll write down Fehling's myself. Fehling's test, and if you got, what will happen is you'll get a blue solution. We'll go to a brick red precipitate if there is any aldehyde present. Okay, and that is the last question on the paper.